Hi, Jemason Tutorials. In this session, we focus on further mathematics and the topic is rotational dynamics. The question reads, a uniform rod AB has mass 2m and length 4a. Roman 1, show by integration that the moment of inertia of the rod about an axis perpendicular to the rod through A is 32/3ma squared. The rod is initially at rest with B vertically below A and is free to rotate in a vertical plane about a smooth fixed horizontal axis through A. A particle of mass m is moving horizontally in the plane in which the rod is free to rotate. The particle has speed v and strikes the rod at B. In the subsequent motion, the particle adheres to the rod and the combined rigid body Q consisting of the rod and the particle starts to rotate. Roman 2, find in terms of V and A the initial angular speed of Q. At time t seconds, the angle between Q and the downward vertical is theta radians. Roman 3, show that theta dot squared equals kg/a into cos theta minus 1 plus 9v squared over 400a squared, stating the value of the constant k. Find in terms of a and g the set of values of v squared for which Q makes complete revolutions. When Q is horizontal, the force exerted by the axis on Q has vertically upwards component r. Roman 5, find r in terms of m and g. All these are max allocations for the various parts, and this was a past exam question from OCR M4. That's a mechanics syllabus 2016. This is a British examination board. It has questions similar. The syllabus is very identical to the GCE syllabus. I was interested in the question because it tests a lot of things under rotational dynamics. So we can learn a lot of things from this question. So in the first part, we have a rod AB of mass 2m and length 4a, and we are required to show by integration that the moment of inertia of the rod about an axis through A, that is through one end, is 32/3ma squared. Okay, in Roman 1, we are required to find the moment of inertia of the rod by integration. The rod is supposed to be AB, and the principle behind finding the moment of inertia of a rod by integration is dividing the rod into an infinite number of elements and finding the moments of inertia of these elements and then summing them up. The fact that you are supposed to find a sum then brings in the notion of integration. So actually, to start, we divide this rod into very small elements, many of them, an infinite number of them, each of length delta x and distant x from the axis of rotation. Remember, the axis is perpendicular to the plane of the rod and passing through A, which is one end of the rod. So if I have now to find the moment of inertia of each of these elements, remember there is an infinite number of them throughout the length of the rod. I would show one just for simplicity in order not to make the diagram clumsy. They actually start from here at the axis and span the whole length of the rod till the end there at B. If I have to find the moments of inertia of the elements, I would need to know the mass of each element. And to find the mass of each element, we have to make use of the property of the rod which they have mentioned in the equation, the fact that it is of uniform mass. If it is of uniform mass, it means the mass is evenly distributed. And so if we have mass per unit length of the rod, we can extend it to find that of the element of the rod. So we start by letting the mass per unit length of the rod to be lambda. So that lambda should be the mass of the rod, which is 2m over the length of the rod, which is 4a, giving m over 2a. We can now say elemental mass. That means the mass of an element of the rod. Elemental mass, since it's so small, we'll call it delta m, which should be mass per unit length, lambda times the length of the element, which is supposed to be delta x. And that should give m over 2a, which is the lambda, times delta x. Once I have the elemental mass, I can now find the elemental moment of inertia. Elemental moment of inertia, I will call it delta I. Again, it's a small amount. That should be equal to the small mass times the square of the distance from the axis of rotation. Each element is distant x, so it should be x squared. And delta m from up is supposed to be m over 2a delta x, so that gives m over 2a delta x, and then x squared. We now say, but moment of inertia of rod equals the sum. So we say summation from x equals 0 from the beginning of the rod where the axis is right through to the end B, which is supposed to be where x is 4a, of the delta I now gives you the moment of inertia of the rod. So to have the moment of inertia of the rod now, you sum up all the moments of inertia of the elements right from the axis at A where x is 0 till the end B where x is 4a. So that is what has been written here. That should give us summation from x equals 0 to 4a of delta I, which is all this statement up here. Write m over 2a x squared delta x. I can now bring in integral, so I take integral from x equals 0 to 4a, so 0 to 4a of m over 2a x squared dx. M all over 2a is a constant, so it goes out, and then when I integrate x squared with respect to x, I get x cubed all over 3 from 0 to 4a. When I substitute, I get 4a all cubed divided by 3 minus 0. The substitution of the lower limit gives 0. And so we get m all over 2a. 4a cubed should be 64a cubed all over 3. And this gives 2 cancels 64 to give 32. A cancels a cubed to give a squared. And so we have 32 all over 3 ma squared. We say therefore I rod about A equals that as required. And that is what the question asks us to prove for 4 marks. In the next part, the rod is initially at rest with B vertically below A, and it is free to rotate in a vertical plane about a smooth fixed horizontal axis through A. A particle of mass m is moving horizontally in the plane in which the rod is free to rotate. The particle has speed v and strikes the rod at B. In the subsequent motion, the particle adheres to the rod and the combined rigid body cure consisting of the rod and the particle starts to rotate. In Roman 2, you have to be very careful. We are told that when the rod is vertical, a particle of mass m strikes it at B and then adheres to the rod. And we are now asked to find the initial angular speed of the system. This is a very delicate situation that you need to handle with care. Usually the best way to analyze a system that is complicated like this, once there is adherence of a particle onto a body and there is rotational motion of the system, it is always good to consider the moment of inertia of the system and to calculate the new center of gravity of the system and analyze the body as a whole rather than doing the analysis of the particle and the body separately. So you first find the moment of inertia of the system and then find the center of gravity of the system. And from there now the analysis would be easier than doing the analysis of the particle and the body individually. So here I start with I system equals I rod plus I particle. So the moment of inertia of the system is equal to the moment of inertia of the rod plus the moment of inertia of the particle about the same axis. The moment of inertia of the rod, well, just from finding it by integration, so we just put it down, 32 all over 3 ma squared plus the moment of inertia of the particle. The particle is said to be found at the end B, so and is at a distance of 4a from the axis A. And so moment of inertia, which is supposed to be the mass, which is m, times the square of the distance from the axis of rotation. So we get 32 all over 3 ma squared plus 16 ma squared. 3 times 16 gives 48 plus 32, 80 all over 3 ma squared is I system. We need it for the analysis of the rest of the question. Now we also need the center of gravity of the system. I will draw the system horizontally first in order to get the center of gravity. So this is the axis at A, and at B the particle is attached. The weight of the particle is supposed to be mg, and the center of the rod is at G, the center of gravity of the rod, and so the weight of the rod is acting at that G. The mass of the rod being 2m, the weight should be 2 mg. Once the particle attaches itself at B, the center of gravity shifts to somewhere between G and B, and we can call that new center G prime. Let it be distant x from the center of the rod. means from that G prime to B should be 2a minus x. Remember, the rod is of length 4a, so from A to G is 2a, and so from G to B should also be 2a. If from here to G prime is x, then from G prime to B should be 2a minus x. My aim is to find x, because when I find x, I will be able to get now the distance from A to G prime, which would become my radius of rotation. It is the radius of rotation because once the system begins to rotate, it is like the rotation of a particle of mass 3m. The mass of the system is concentrated there at G prime. So if the system begins to rotate, it is equivalent to the mass of 3m. That means the mass of the system, which is acting at that G prime and is distant from A by a distance which should be 2a plus x. I need to find that distance. That distance becomes my radius of rotation. So that is where the secret of the problem is. If you are able to get that radius of rotation correctly, then your analysis will not have any problem. And so to have this x, which will help me to get the distance AG prime, which becomes my radius of rotation, I will take moments about G prime. So we say taking moments about G prime, we have 2mg times the perpendicular distance from G prime, which is x, should be equal to mg times the perpendicular distance from G prime, which is 2a minus x. The mg's will cancel, and then I have 2x equals 2a minus x, so that 3x would be 2a, and then x would be 2a all over 3. Therefore, AG prime should then be 2a, from A to G is 2a plus the x, which I'm just from getting, which should now be 2a plus 2a all over 3. 3 times 2a, 6a plus 2a, that gives 8a all over 3. So this is my radius of rotation when I start doing the analysis of the system. With the moment of inertia of the system and then the radius of rotation obtained, I can now begin the question proper. We are told that when the system is vertical, with B vertically below A, a particle of mass m moving with speed v strikes the rod at B and adheres to it. And we are now being asked to calculate the initial angular speed of the system immediately after impact. So in order to find that angular speed, I will need to use the principle of conservation of momentum. So by the principle of conservation of angular momentum, I would have that initially it is the particle that is doing the motion. The rod is stationary initially, so the initial angular speed of the rod will be 0, and the initial angular speed of the particle is actually its moment of momentum. Remember, it's moving with linear speed, so we have to use linear momentum in conservation of angular momentum. Then we are going to use but its moment of momentum. So we are going to say moment of momentum of the particle, which is actually the linear momentum times the perpendicular distance from the axis of rotation, which is 4a, Don't forget the particle hits the rod at B and the axis is at A. So the whole distance from where that collision takes place to the axis is the length of the rod, which is 4A, plus 0. That means the momentum of the rod initially was stationary, so the momentum is 0, equals, once the particle adheres to the rod and the system has to begin rotational motion, we can now get the total angular momentum of the system, which is supposed to be I omega. Moment of inertia times angular speed would give you angular momentum. And so we should have 4 mva equals I system from up is supposed to be 80 all over 3 ma squared omega. We are asked to find omega in terms of v and a, so m's will cancel, then a would cancel the square of a there. When you cross multiply, you should have 12v equals 80a omega, so that omega should be equal to 12v all over 80a. Therefore omega equals, dividing by 4, we get 3v all over 20a. That is the angular speed of the system immediately after impact. So in Roman 3, we are asked to prove that theta dot squared equals k g over a cos theta minus 1 plus 9 all over 400a squared, stating the value of the constant k for 4 marks. When you are dealing with moment of inertia, especially applications of moment of inertia, and a system is rotating, if there is a proof that involves theta dot squared with cos theta or sin theta in the expression, know that you would get that proof by the conservation of mechanical energy of the system as it is rotating. So we are going to get that proof in Roman 3 by the conservation of mechanical energy. We consider again the initial position of the particle, the initial position of the system, in which A was up there and B down. Then the system had its weight concentrated at G prime, and that weight was now 3 mg, because there was the rod of mass 2m and the particle of mass m, and that system was at a distance of 8a over 3 from the axis of rotation. We would be needing that in order to find the potential energy of the system as we are conserving energy. We need also to define the potential energy equals 0 level. When the system begins to rotate at some point at time t, we have the axis again at A there, and the system finds itself in this position, where again we have G prime, distant 8a on 3 from the axis of rotation. There is the weight which is acting 3 mg vertically down. The angle is said to be with the downward vertical, which is theta. This distance from the 0 level where the weight of the system is acting, we need it. It is h. And we are supposed to use it again as we are calculating the potential energy of the system. The angle here with the upward vertical, so this one is with the downward vertical, this other one is with the upward vertical, is equal to this other one. Remember, this line is parallel to this one, so these are alternate angles or z angles. They are always equal. If I want to find this h, then this is the hypotenuse of a right angle triangle. I will have to use cos theta on this side here to get it, which is 8a over 3, the hypotenuse times cos theta. I would need that height at some point, so I can now conserve mechanical energy. Remember, at this position, the system is rotating with angular speed theta dot. In the initial position, now mechanical energy is supposed to be composed of gravitational potential energy, kinetic energy, and elastic potential energy. But elastic potential energy does not apply here. So we only have kinetic energy and potential energy. Initially, the potential energy is negative 3 mg, that is the weight times the height of the weight from the p equals 0 level, and that height is 8a all over 3. Remember, G prime is below the potential energy equals 0 level. That is why the potential energy is negative. We also have the initial kinetic energy, and when a system is rotating, kinetic energy is given by half moment of inertia times the angular speed squared, and the angular speed initially was omega. That should be equal to, again, the potential energy at this other position should be negative 3 mg. That's the weight of the system times the distance from the 0 level, which is 8a all over 3 cos theta, plus again half I. This time the angular speed is no more omega. Omega was the initial angular speed, which was constant at this point. At this point now, it is the general angular speed, which is changing with time. So at time t, it should be theta dot squared. Now, from Roman 2, we have that the moment of inertia of the system was 80 all over 3 ma squared, and omega was 3v all over 20a. So in the next step, I can cancel the 3's and I'm left with negative 8 mg a plus half into 80 over 3 ma squared into 9v over 20a, all that squared, equals 3 cancels 3 here, negative 8a, mga cos theta plus half into 80 over 3 ma squared theta dot squared. And we can simplify things. M and a cancel. M and a, the square of a will cancel there. M and a will cancel. M and the square of a will cancel. So I'm left with negative 8g plus half of 80 is 40 all over 3a. This was supposed to be 3v squared, so squaring will give into 9v squared all over 400a squared equals negative 8g cos theta plus 40 over 3 a theta dot squared. In the proof, we are asked to show that theta dot squared equals k g over a cos theta minus 1 plus 9v squared over 400a squared. And this 9v squared over 400a squared is appearing in my step that I'm just from obtaining here. So I make sure I don't distort it as I'm arriving the next step. So my aim now is to make theta dot squared the subject. So I copy it this way. 40a all over 3 theta dot squared should be equal to, I now send this other term to make these other ones. I begin with it 8g cos theta, then minus 8g, then plus 40a all over 3 into 9v squared all over 400a squared. And I can divide through now by 40a over 3, so that I get theta dot squared equals 8g is common into cos theta minus 1 all over 40a all over 3 plus, dividing here again by 40a over 3, we are just left with 9v squared all over 400a squared. And simplifying now, we'll get theta dot squared equals 3 will spring up, while 8 will cancel 40 to give 5. So we'll get 3 all over 5 g over a into cos theta minus 1 plus 9v squared all over 400a squared. And that gives the proof. In the proof, this 3 over 5 is k, and we are asked to state the value of k. So we say as required, where k equals 3 all over 5. In Roman 4, we are asked to find in terms of a and g the set of values of v squared for which Q makes complete revolutions. In the case where Q makes complete revolutions, we would have the situation where the system rotates and the axis, which is here, B, now finds itself at the top there. Remember, the initial position was down this way. B was here. So the rotation has taken place until it finds itself now at this top, vertically above A. For this to happen, it should be the case where the system should have turned an angle pi from here to arrive here where the system first becomes vertical. It should have turned 180 degrees, which is pi radians. That's the first condition for the system to make complete revolutions. The next condition is that by the time it is making that angle pi radians, the angular speed theta dot should be greater than 0 at that point. So when it makes angle 180 degrees, which is pi radians, just at that point where the angle is 180 degrees, the angular speed should be greater than 0. The system will now be able to cross this boundary here and move down under its own weight to make a complete revolution. So that is the two conditions for complete revolutions to take place. If I come back here now, I will now say if theta dot is greater than 0, then theta dot squared would also be greater than 0. And that implies that 3g all over 5a into cos. The cos theta at that point should now be the cosine of pi, which is here now minus 1 plus 9v squared all over 400a squared. And we have that cos pi is supposed to be negative 1, so negative 1 minus 1 will be negative 2, so we get negative 6g all over 5a plus, so this is greater than 0 there, plus 9v squared all over 400a squared should be greater than 0. and 9v squared all over 400 a squared should be greater than 6g all over 5a. We are looking for the set of values of v squared, so v squared should be greater than 6g all over 5a times 400a squared all over 9. V squared should be greater than, if we cancel 5, even a cancels the square, and then 5 will cancel 400 to give 80, 3 cancels 6 to give 2, and here to give 3. Overall 2 times 80 10 times ag, that makes 160 ag all over 3. And so this is the set of values of v squared that they are asking. That was supposed to be Roman 4. Roman 5, we are told that when Q is horizontal, the force exerted by the axis on Q has vertically upward component R. And we are asked to find R in terms of M and G. So when the system is horizontal, we are at this point. If there is a component of the reaction that is vertical, then we are talking of this. And G prime is supposed to be acting here. So that there is a component, the weight now is acting vertically down, which is supposed to be 3 mg. And when the system is in this position, remember the distance from A to G prime is supposed to be 8a over 3 from previous work. And in order to find R, we need to resolve perpendicular to AG prime. In this position, we have a tangential acceleration, which is given by r theta dot dot, and r in this case is 8a all over 3 theta dot dot. So when we resolving perpendicular to AG prime, the acceleration is upwards, remember, so the forward force should be this R that we're looking for, and the backward force should be 3 mg. So we can be talking of R, Newton's second law, minus 3 mg equals 3m, the mass times the acceleration in the vertically upward direction, which is 8a over 3 theta dot dot. And we have that R should be equal to 8 ma theta dot dot plus 3 mg. Now what we need to find is theta dot dot, and to have theta dot dot, I need to make use of this proof here, the expression for theta dot squared. So we're going to differentiate both sides with respect to t. So d over dt of theta dot squared should be equal to d over dt of 3g over 5a cos theta minus 1 plus 9v squared all over 400a squared. To differentiate theta dot squared, I have to use the power rule. because I'm differentiating the function of a function. So theta dot squared differentiated gives 2 theta dot, and then I differentiate theta dot with respect to t, which gives theta dot dot. That's the power rule. Equals, on the right hand side, I'm differentiating with respect to t, but the expression I have there is in terms of theta. Remember, GA, the V's, and the rest are all constants. So theta is the only variable there, but I'm differentiating with respect to t. So I will first have to differentiate with respect to theta and then multiply by d theta dt according to the chain rule. So that I get now 3g all over 5a. The differential of cos theta is negative sine theta, and the differential of negative 1 is 0. The differential of 9v squared all over 4a squared with respect to theta is 0. That's a constant, so the differential is 0. Then I multiply the answer by d theta dt. And d theta dt is simply theta dot, which will cancel this other one. And so my theta dot dot should be 3g all over 10a. I divide through by 2, so I get 10a at the denominator of negative sine theta. Now, when the system is horizontal, remember it was rotating from this position. When it is horizontal, my theta now is 90 degrees. So when it finds itself at the horizontal position, theta is 90 degrees, or pi on 2, since we were dealing with radians in this case. So we now say, but theta equals pi on 2. We now have theta dot dot to be 3g all over 10a sine pi on 2. Well, it's negative, sorry, which gives negative 3g all over 10a. Therefore, R equals, we go back to the statement that we were looking for R, 8ma into negative 3g all over 10a plus 3mg. That a cancels a, and we are left with the simplification, which is negative 12 mg all over 5 plus 3mg. 5 times, that's 15 minus 12, 3mg all over 5. And that is the component of reaction that's pointing vertically upwards as the question specified in terms of m and g.